So in the last lecture, we were discussing about hydrostatics, that is the physics of a fluid which is at rest, including the concept of pressure gradient that we had seen and the concept of Archimedes principle, Pascal's law, etc. Archimedes principle gave us the formula for buoyant force acting on a body which is submerged in a fluid, whether it is partially submerged or fully submerged. And from that, we also saw the physics of a floating object in a static fluid. Now, today we will come to the second part of fluid mechanics, in which we will be discussing about the physics of a fluid in streamlined motion or in steady flow and related applications. So let's begin. So this second section of fluid mechanics is called hydrodynamics. So in this section, we'll be studying the physics of a fluid. And by a fluid, we mean an ideal fluid here. In motion, but by motion, we mean a particular type of motion called steady flow. Or we'll see later, also called streamlined motion. So remember the concept of ideal fluid or the meaning of the term ideal fluids is that they are fluids which are first of all incompressible. It means they have a uniform density. Independent of pressure. And secondly, they are non-viscous. That is negligible coefficient of viscosity. Okay, next up, let us understand steady flow, or what is also called streamline motion. So steady flow is the type of motion of an ideal fluid which is such that the motion of a fluid element is non-turbulent, irrotational, and along well-defined paths or trajectories called streamlines. You can say it has these three important properties: non-turbulent, irrotational, and along well-defined paths, which we call streamlines. So just note down this definition, then I'll explain each of these points. Okay, so let us understand this in more detail. So turbulent motion versus non-turbulent flow. So what happens in turbulent flow is that fluid elements will experience sudden changes in pressure due to high velocity collisions during their flow or motion. Whereas non-turbulent flow is that is the type of motion where fluid elements do not experience any high velocity collisions. And therefore, their path or trajectory is well defined. It means there are no sudden changes. And the pressure gradient is gradual. That means there's no sudden change in pressure during their motion. So this is best understood with examples. Example of a non-turbulent flow is something like this. Liquid flowing gently through a pipeline, not at too much velocity. Okay, so the slope of the pipeline is gradual, whereas an example of corresponding turbulent motion is, let us say, the motion of an extreme kind of waterfall. So if you notice here, there is collision, there is, as a result of the collisions, so water flowing rapidly down a steep waterfall. So there is turbulence due to high velocity collisions. So what happens during turbulent flow is that, first of all, the motion of the fluid elements, that is small volumes of liquid, if you follow their path, It's not predictable because they are going to undergo random and extreme collisions. And secondly, as these volume elements flow along in the turbulent flow, they will be subjected to extreme changes in pressure, sudden and extreme changes in pressure. Whereas in steady flow, that is not happening. There is a gradual change in pressure as they flow through a sort of streamlined motion. That is, they are moving along well-defined paths, not along unpredictable paths, because there are no sudden collisions which are happening. Now, similarly, let's come to the second point of irrotational flow. So, irrotational motion of fluid elements means that any volume element of fluid will not undergo rotation while moving. So, not undergo rotation means that the volume elements will be in pure translation. So again, the example of that is if you consider water flowing gently through a pipe, you can see that any volume element of fluid, like imagine a cylinder of fluid. So this is delta V volume. It has this kind of a path. As it is moving, you see that it's in translational motion. It's not in any kind of rotational motion. So it is in irrotational motion. So that is another important property of steady flow. A very extreme example of a fluid in turbulent and rotational type of motion is smoke coming out of a chimney. Okay. Now, smoke is a gaseous mixture with suspended particles, so it can also be treated like a fluid, but it is definitely not an ideal fluid because it is highly compressible. So, smoke coming out from a chimney, if you just observe how the volume elements of that move, you will realize that they are, first of all, smoke is a non-ideal fluid because it is highly compressible and also viscous. So this kind of a situation, as it comes out of the chimney, volume elements of smoke experience highly turbulent and rotational plus translational motion. So that means within the smoke column, if you track a certain volume of fluid or smoke, it will undergo a kind of unpredictable zigzag kind of path. Okay. And while it is going through that zigzag kind of path, it might experience collisions. So it will have a motion which is a combination of linear motion and rotational motion. Okay, so this is the counter example of a fluid undergoing a completely opposite of what is called the streamline motion. Okay, because it is highly turbulent and it is also rotational in character. I mean, rotational plus translational mode. Okay, now the final property, the third and final property of steady flow or streamline motion was that fluid elements in streamline motion move along well defined and fixed paths called streamlines. So the way to understand this is that if we consider an ideal fluid in steady flow, what is happening is that we will see any particular volume element it is moving along a path like this, such that as it is moving, there's a well defined, not a zigzag kind of path. And one of the consequences of this is that one of the consequences of this is that any fluid element, by fluid element, of course, we mean a differential or very small volume of fluid. You can treat it like a particle. So any fluid element at a given instant has an identical velocity to the fluid element, okay, which was at the same position at a time before. Okay. So basically, if a fluid element at some time t equal to t is at a certain position, it has a certain velocity. Now this velocity will be the now at a new time. Okay. This fluid element might have moved somewhere forward. And some other fluid element which was behind it in the motion has come and occupied that position now. Okay. So that fluid element has come here. But this fluid element will have the same velocity as a previous fluid element that was at that position at any other time. So that means, okay, so this basically also means that in steady flow, at a particular cross section of the flowing liquid, okay, all fluid elements going through that cross section have a fixed amount of velocity. By fixed amount of velocity, we mean that at any moment of time, if we see all the fluid elements passing through that particular cross section, they will always pass through that cross section with that fixed value of velocity. So at any cross section of the fluid in steady flow, the flow velocity is constant for all elements crossing it at all times. So this is the meaning of saying that as a consequence of this, we will see that fluid particles or fluid elements, they move in such a way that they are following each other along well-defined paths. It's a sort of ordered motion where a fluid element cannot undergo a zigzag path and cannot undergo rotation while going along that path. It has to go along a very well-defined linear predicted kind of path where it is just following the particle in front of it or following the fluid element in front of it exactly in the same way as that one is moving. So the consequence of this is that fluid elements move in an ordered well-defined path such that each element moving along a streamline simply follows the element in front of it in identical motion. The trajectories along which fluid elements flow are called streamlines, and hence the term streamline motion. Now we'll see some properties about streamlines. So first of all, streamlines do not ever intersect. Secondly, at any point, the direction of the velocity vector is given by the tangent to the streamline. Okay. So at a point like this, for example, the velocity vector, its direction will be along the tangent at that point. At a point like this, the velocity vector will be like this. At a point like this, the velocity vector would have become like this, because the tangent at that point is like that. And the third point, as you can see, that streamlines are more closely packed at positions of smaller value of cross section and more loosely packed at larger cross sections. For example, in this diagram, you can see here the cross section is comparatively lesser, so the packing density is more. The streamlines are closer together, whereas comparatively here, the area of cross section is more. So you can see the streamlines are further apart. They are not packed so closely. Okay. So these are certain important properties about streamlines. Now we come to the mathematical equations that we can write for steady flow or streamline motion. So the first is called the equation of continuity. Which is applicable strictly to steady flow. Which is the same thing as streamline motion. They are one and the same, steady flow and streamline motion. So the equation of continuity is understood like this, that if you compare any two cross sections of area A1 and A2 like we drawn earlier, then the product of area of cross section into velocity of flow will be the same. So here if the area of cross section is A1 and the fluid elements passing through that cross section have a velocity of flow of V1, whereas here if the area of cross section is E2 and the fluid elements coming from that cross section or crossing across that cross section have instantaneous velocity V2, then A1 V1 will be equal to A2 V2 for points at any two cross sections in the fluid in motion. So another way of expressing the continuity equation is that the product of area into velocity is uniform at all points. So just make a note of this. So we'll quickly see an example problem. This. So suppose this is water coming out of an open tap, but coming out gently in comparison, not flowing very rapidly. So if the velocity of flow, so if I consider 2 points, so water flowing vertically down from an open tap, but the flow is gentle. It is not at high pressure. So if at the point A, the cross section is 4 centimeters square and the velocity of flow is 50 centimeters per second, and at the point B, the cross sectional area is become 2 centimeters square and velocity of flow is V2. Then find the value of this V2, and secondly, the volume flow rate, that is delta V by delta T, where delta V is volume and not velocity, in cubic centimeters per second of water. What is the rate at which water is flowing in this particular case from the tap as water is flowing down? What is the volume rate at which it is falling down? That is the number of cubic centimeters per second of water that is flowing through that pipeline. Just try this out. Okay, very good. That's correct. So let's understand the first thing, the application of continuity equation. So from that we will get 4 centimeters square into 50 centimeters per second should be equal to 2 centimeters square into V2. So we'll get V2 as 100 centimeters per second. All of you should have got this correct, but I've got the answer from only 3 people. Okay. So others who have not sent me the answer or not worked out the question, please make sure you understood how to apply this very simple equation. All you have to do was equate A1 V1 with A2 V2. Okay. Now what about the volume rate of flow? How we will calculate that? Let's look at that next. So volume rate of flow. Delta V by delta T is given by area of cross section into velocity, because area of cross section is in centimeters square, velocity is in centimeter per second. So therefore product of area into velocity will give me delta V by delta T in centimeter cube per second. Okay. So in this case A1 V1 is equal to A2 V2 is equal to A into V at all points. Okay. And that product is equal to 100 centimeter cube per second. So volume flow rate is 100 centimeter cube per second. So that is why we say that another way of expressing the continuity equation is that the volume flow rate is constant throughout the liquid. Product of area into velocity is the same thing as volume flow rate, and that should be constant. Okay, so this is about application of continuity equation in an example. The next thing is another important mathematical equation for steady flow, and that is something called Bernoulli's equation. Okay, so this is an equation that relates the following quantity. pressure, okay, flow velocity, okay, and height with respect to some reference level. Okay, so it relates these three quantities P, V, and H at any point inside an ideal fluid in steady flow. So we will see the statement of Bernoulli's equation next. So as usual, if this is a tube or a pipeline through which liquid is flowing gently in streamline motion, but it's having variable cross-sectional area, and also it is not a horizontal pipe, it is in general a pipe which is in a vertical plane. So in this pipe now, if we consider any position like this, let's say, which has cross-sectional area A1, at this point the velocity of flow is V1 and the internal pressure here is P1, and also the height level of that cross section from my reference level which I've drawn below is H1, and like that I consider another cross section, let's say here, of area A2. Now liquid flowing through this cross section has velocity V2, it's at pressure P2, and the average height at this point is at this cross section is H2. Then according to Bernoulli's equation, the value of pressure plus half rho V square, where rho is the density of the fluid, plus rho GH. At any 2 points, the sum of these three quantities should be equal. Okay. So this is one way of expressing Bernoulli's equation. Or another way of expressing it is that in general, the sum of pressure plus half rho V square plus rho GH is a constant, where of course rho is the density of the fluid. So just make a note of this and we'll understand the applications. Okay, so let's understand a few points about this first. Okay. So first of all, each of the terms, pressure, half rho v square, and rho gh, have dimension of energy per unit volume. If you look at the dimension of pressure, it is equal to the dimension of half rho v square, equal to the dimension of rho gh, equal to dimension of energy divided by dimension of volume. And you will see that is this much. So therefore, P is called the pressure head. Okay. Half rho v square, it is called the kinetic head because it is kinetic energy per unit volume. And rho gh is called the gravity head because it is gravitational potential energy per unit volume. So as you can see from this explanation below, that Bernoulli's equation is a sort of application of work energy theorem, but instead of relating energies, we are relating energy per unit volume. And instead of work done, we are relating pressure. Okay, so hope it's clear up to this point. Okay, now let us understand a sort of derivation behind Bernoulli's equation. Okay, so this derivation is not necessary from exam point of view, but it is just for your own understanding. Of course, it is necessary from your board exams point of view or from your semester exams point of view, but it's not necessary for CET or JEE Mains. So I'm just explaining the derivation in short over here, but also make sure you go through the steps from your respective textbooks. So to understand the derivation of Bernoulli's equation, what we will do is we will first consider a certain section of fluid that is bounded by these two areas A1 and A2, where the velocity of flow here is V1 and the velocity of flow here is V2. In the earlier diagram, we might have interchanged A1, A2, but it doesn't make a difference. Okay. Whichever cross section we call A1 and whichever cross section we call A2. Now, from a certain standard reference level, which is some horizontal plane, this area is at a height of H1, and this cross section is a height of H2. Now, this we are considering at a time t equal to t. Now, very short time later, at t plus delta t, this whole body of fluid has moved somewhere here like this. Okay. It has moved to this new position where the displacement of this cross section of fluid will be V1 into delta T, and the displacement of this cross section of fluid will be V2 into delta T. Okay. Also, the fluid pressure here is P1, and the fluid pressure here is at this cross section is P2. So now when we consider this cross section of fluid, you can see that it is experiencing force F1 from this side, which is P1 into A1, and it's experiencing force F2 from this side, which is P2 into A2. Okay. So during time interval delta T, okay, the work done on that volume element, okay, due to pressure, that will be how much? Now you can see that this section where F1 is acting is moving in this direction by a displacement of V1 delta T, whereas this is moving in the same direction as the force as V2 delta T. So F1 is doing negative work, okay, whereas F2 is doing positive work. Okay. And we can see that this is P1 A1 V1 delta T, P2 A2 V2 delta T. So in the next step, we will see that if we apply continuity equation, so from equation of continuity, we can see that A1 V1 is equal to A2 V2 is equal to volume flow rate. Okay. So therefore, A1 V1 delta T is equal to A2 V2 delta T is equal to the volume of liquid that flows through in that small time d delta T. Okay. So this work done can be written as P2 minus P1 into delta capital B. So this is the work done in time delta T, where delta V is the amount of volume flowing through the pipe in time delta T. So that becomes this. So just make a note up to this step. Then we'll discuss the kinetic head, how it will come, and then finally the gravity head, how it will come. Okay, now next up, let us consider the change in kinetic energy of this volume element. Okay. In time delta t. So what is happening is you can see that within the pipeline, this volume element was like this at the initial time t. Okay. Now a short time later, it has become, just a minute. So a short time later, the volume element has become like this. Okay. Yeah, so I'll have to draw it here only. So if you compare how this volume element has changed its position and therefore its velocity profile. Okay. So comparing this diagram below with this diagram above, this is at t equal to t, this is at t plus delta t. So if we superimpose these two diagrams, like it is in the original diagram, if we superimpose them, you will see that to this volume, it's like this volume has got added and this volume behind has got subtracted. So there is a section here which has got added and there is a section here which has got subtracted. So the change in, so this section which has got added here, let's say its mass is delta m1 and its speed is v1. Whereas this section which has got removed, let's say its mass is delta m2, but its speed is v2. Okay. Now you'll see that this delta m1 is actually equal to delta m2 because of continuity equation. Okay. So delta m1 is equal to delta m2, which is density into that volume, because delta m1 is density into a1 v1 delta t, and delta m2 is density into a2 v2 delta t. And we know that a1 v1 delta t is equal to a2 v2 delta t is equal to that volume that is flowing through the pipe in time delta t. Okay. So the change in kinetic energy in time delta t, just a second.
Mm. Mhm.
Yeah, sorry about that. So the change in kinetic energy you can see is, now if you compare this picture with this picture, na, so here compared to the kinetic energy initially, whatever this kinetic energy was, if this one has some final kinetic energy, so from this diagram you can understand that this final kinetic energy is equal to the initial kinetic energy plus the energy of this section. So that is half delta m1 v1 square, but minus the kinetic energy of this section, because when you superimpose this, it's like this mass delta m1 has got added and this mass delta m2 has got subtracted. Of course we know delta m1 and delta m2 are the same, but their kinetic energies are different because v1 and v2 are not the same. Okay. So coming back to this change in kinetic energy, you can see that from this delta ke is final kinetic energy minus initial kinetic energy. Okay. So that quantity from above you can see is, we are adding this section's kinetic energy, but we are subtracting the section behind that one's kinetic energy. Okay. Now we know that delta m1 is equal to delta m2, so we'll substitute this over here next. So this will become half into rho into delta v. Okay. So this factor becomes common into v1 square minus v2 square. Okay. So this becomes the change in kinetic energy in time delta t for this section. Okay. So this is the second term of our work energy equation that we're going to develop, that the change in kinetic energy is so much. So we're going to relate the work done with the change in kinetic energy plus the change in gravitational potential energy. So these two things we have just seen. Now this is the next thing we have to calculate. So you can see we'll use a very similar method to calculate the change in gravitational potential energy. We can see that from this diagram itself. So यहाँ पे from the common reference level, this section has height h1, this section has height h2. So the change in gravitational potential energy, that is equal to the gravitational potential energy of this part which is getting added plus delta m1 gh1, but minus the gravitational potential energy of this second section which is getting subtracted. Okay. So again we use this relation over here, that delta m1 is equal to delta m2. So doing that, we can see that the change in gravitational potential energy becomes density into that sectional volume delta V into G into H1 minus H2. So this is the change in gravitational potential energy in time delta T. This is the change in gravitational potential energy in time delta T. This was a change in kinetic energy in time delta T. Okay, so finally now when we merge these quantities into our work energy theorem, that work done is equal to change in kinetic energy plus change in gravitational potential energy, we will see that we'll get this relation that P2 minus P1 delta V is half rho delta V into V1 square minus V2 square plus rho delta Vg into H1 minus H2. So cancelling out the common terms, we can see that P2 minus P1 is half rho V1 square minus V2 square plus rho G into H1 minus H2. And now just keeping the terms of index 2 on one side and index 1 on the other side, we can see that P2 plus half rho V2 square plus rho GH2 is equal to P1 plus half rho V1 square plus rho GH1. You can see that Bernoulli's equation actually comes from a statement of work energy theorem. And since we can select any 2 points arbitrarily, so this equation holds for all points, not just 1 and 2. So in general, we can say the sum of pressure head plus kinetic head plus gravity head at any point inside the liquid is constant. This is another way of expressing the Bernoulli's equation. Okay. So you can note this down and let's look at a quick application example of this. So suppose we are having tapering kind of pipe like this, inside which liquid is flowing like this. So if at this point the velocity is v1, at this point the velocity is v2, at this point the area of cross section is a1, at this point the area of cross section is a2. Okay. So this is water which has density of 1 gram per cc. If a1 is equal to say 12 centimeters square, a2 is equal to 4 centimeters square, v1 is equal to 20 meters per second, then find v2, and secondly the pressure difference P2 minus P1. The pressure at the 2 points P1 and P2, the difference between them. This is a horizontal pipe. So we'll quickly see the application of Bernoulli's equation along with continuity equation in this. And with that, we will conclude today's session. Okay, so if you compare these 2 points, first thing that you can notice is that A1 V1 is equal to A2 V2, which is equal to the volume flow rate. So obviously my V2 will become 3 times V1 because A2 is 1/3 of A1 that you can see from this data. So V2 will become 60 meters per second. That's the answer to the first part. Okay, next we have, so this is continuity equation. Next, we apply Bernoulli's equation. That is P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. So first thing we notice here is that H1 is equal to H2 because it's a horizontal pipe. So the height level with respect to some reference ground level at both these points 1 and 2 that you can see, point 1 is here, point 2 is here. So they are at the same height with respect to any reference level. Okay. So these two terms will cancel out. So next we will notice that P1 plus half rho V1 square is equal to P2 plus half rho V2 square. So now we can see the pressure difference between these 2 points, P1 minus P2, can be equated with half rho P2 square minus V1 square. So this pressure difference which we wanted to find out is half into density of water. 1 gram per cc we will convert to 1000 kg per meter cube into V2 square, which is 60 square, minus V1 square, which is 20 square. So this will give us the pressure difference in the SI unit of pascals. Let's check out how much this is. This is 500 into 10 raised power 2, we can take common. So 36 minus 4. 5 into 32 into 10 raised power 4. So 1.6 into 10 raised power 6 pascals. This is the pressure difference. And that pressure difference is such that you can see that P1 is greater than P2. So P1 will be equal to P2 plus so this becomes the second part's answer. Or you can say if we are calculating P2 minus P1, it is a negative quantity. So this is the completion of the theory part of fluid mechanics. Next lecture, we will look at some more examples, numerical examples of application of Bernoulli's and continuity equation. But theory wise, we are done with this chapter. Okay. And next chapter we will do after fluid mechanics will be properties of matter, which is also called properties of solids. So that will include the properties of elasticity, Hooke's law, modulus of elasticity, Young's modulus, shear modulus, etc. And eventually after that, we will look at properties of non-ideal fluids, which is basically viscosity and surface tension. So elasticity, viscosity, and surface tension. In general, these are the properties of matter that we'll be studying as part of that chapter next. Okay. So that's it for today's session. People, wish you all the best.